So previous class we discussed concept of Gauss's law and electric flux. Okay, and now we discuss the continuous charge distribution. Okay, so previous class we derived the Gauss's law and Coulomb's law, relation between these two law, and what is the electric flux, and behind the concept of electric flux we discussed. Okay, so now start the today's class, continuous charge distribution. Continuous charge distribution. Continuous charge distribution. So there are the three types of charge distribution. Okay, so one dimensional, two dimensional, and three dimensional. Okay, so one dimensional charge distribution is called a line charge distribution. Two dimensional charge distribution is called a surface charge distribution, and three dimensional charge distribution is called a volume charge distribution. Okay, so first we discuss line charge distribution. Line charge distribution. So the name suggests the line. Okay, means a suppose a conducting wire, like a thicker wire, like a thicker wire, a line. Okay, that thicker wire, a line, and the length is a L. Okay, and so consider the small amount of length. Okay, in line, the small amount of length. This the small amount of length is called a delta L. Okay, and this line contain suppose these all positive charges. Okay, suppose all positive charges here. Okay, now calculate electric field at that point. Suppose here at point P, here we calculate electric field at point P. Now the small amount of line delta L contained the delta Q small amount of positive charge or negative charge. Okay, doesn't matter, it contain a positive charge. Let the assumption here the charge is positive. So now starting graphically, this is the origin point O and the position vector. Okay, position vector of the small length. Suppose these are the position vector is called R. This is the position vector. Actually, okay, take it. Now, and the point P, the position vector is the in relation, that is a called R1 position vector. Okay, and point P, if you see the carefully, these are the all positive charges. Okay, so at point P, electric field goes outward direction. You know that. Okay, so the point P, the position vector of point P from here, we see that this line. Suppose this line is called, suppose center R R1 and that is the R2. Okay, so the line charge distribution and that line charge density. Okay, so line charge density, charge density lambda, that is equal to the charge delta Q amount of charge by small amount of length delta L. If consider that is the total length L and that now delta Q turn into the Q total charge Q. Okay. So now write the notes of line charge distribution. Note that the line charge density, the linear charge density, linear charge density. So density means here charge per unit length actually. Okay, the charge per unit length, the q amount of charge, distributed through through entire wire, and first consider small amount of charge. First consider small amount of charge. Okay, delta q in small length delta L. So we get the equation here, lambda equal to delta q by delta L. That's the line charge distribution. Okay, the electric field. Now that is another important point, and is called another charge distribution is a surface charge distribution. Similar that line charge distribution like. Okay, so first we consider a surface, a two-dimensional actually here. Okay, the two-dimensional means a surface or a area. These are the a paper. Okay, now consider the small amount of surface. These are the small amount of surface. Okay, these are called surface whose name is delta L. Surface is delta L, and the surface contain all positive charge, all positive charge in both sides, front or back, or called charge sheet actually. Okay, now the sorry, no, it's not delta L, actually delta A area. Okay, here is not delta L, that is a delta A. So then delta A area contain delta Q amount of charge. Total charge is Q, and delta A contain delta Q amount of charge. Okay, so similar previous concept of these, suppose the origin point O, the position vector of the surface is now in that direction. Okay, and that is called suppose the R vector, position vector of the surface, and calculate the electric field at that point P. Okay, so that is the, and the positive, so electric will go to outward direction, this charge is positive, so that is called R1 vector, and at point P position vector at point P position, that is in that direction actually, it is called R2. So electric field here E, so that is the final direction. Okay, so here the surface charge distribution, that's name is surface charge distribution. The surface charge distribution here, that's symbol is sigma. The sigma contain the small amount of charge delta Q over that small amount of area delta A. In see that in previous lambda contain small amount of charge delta Q by delta L, that is a length. Okay, that the length, same sigma, that is a delta A area, that is one dimensional, that is a two dimensional area, and that is also Q by A. Okay, and now last is a called volume charge distribution. the volume charge distribution charge distribution okay. So volume charge distribution is similar to surface charge or line charge, like okay, suppose there is considered a 3D object, okay, any arbitrary 3D object, that is a 3D object. Consider the small volume. Small amount of volume, that is a delta V amount of volume, if that is enclosed by all positive charge. So delta V enclose some delta Q amount of charge, this volume. Okay, so starting from origin O, the position vector of that small amount of volume is so suppose now we change that at point origin point O. Okay, suppose that's the position vector is R position vector. These position vector signifies that the position of the unit volume. Okay, actually. Now choose any arbitrary point P here. That point P, calculate the electric field at point P. So if that is a positive, so that's why the electric field goes outward direction. That is R1, and position vector at point P from origin. Okay, that is R2. Okay, so we get that is volume means rho. Volume charge distribution is symbolized by rho. Volume in charge distribution, that is equal to amount of charge enclosed by the small volume delta V, or that we say that is the total charge by volume. Okay, total charge enclosed by total volume. Now if I calculate the EP, okay, if I calculate EP, okay, so delta EP, consider the small amount of electric field, that is also equal to 1 over 4 pi epsilon naught, that is some constant, Coulomb constant K, the delta Q, the source charge, by R square, here the R1 square, the distance from this charge to R1 square, that is called R1 cap direction. Okay, so now delta Q 1 over 4 pi epsilon naught replaced by Q rho delta V by R1 square and R1 cap. That is a delta V small amount of volume. Okay, so if I calculate all volume, to need summation, the superposition principle, the summation need all volume B, there is rho delta V R1 square R1 cap, the direction vector. Okay, now their summation means addition. Say another mathematical tool, the beautiful mathematical tools to help these overcome the multiple number of addition. That mathematical tool name is the integration. Integration means addition. With the help of integration, the beautiful mathematical tools will solve easily actually. Okay, there's a volume integral. There's a rho dv. Now that's delta v turned into dv by r1 square and r1 cap direction, that is delta ep integration, delta turns to d, that is ep. Okay, that's the final expression. Okay, so if I similar that ep for surface, that is a dep 1 over 4 pi epsilon naught, the Coulomb constant, surface integral Okay, that is a surface. Now we see the q, delta q change into sigma delta a. So sigma dA area, differentiate area, r1 square r1 cap. So EP similar at line. Okay, DEP 1 over 4 pi epsilon naught, that is a line. Okay, one dimensional integration, that is equal to lambda DL by r1 square r1 cap. Okay, so first equation signifies for volume charge distribution, second equation signifies for surface charge distribution, and the third equation signifies that line charge distribution. Okay, very easy. So similar that all the charge distribution here. Okay, now we derive the Gauss's law again. Okay, some tricks. Okay, and another methods. Okay, so recall that previous class. Uh, so Gauss's law again. This law is a recall of Gauss's law concept. So Gauss's law, actually what is a Gauss's law and why Gauss's law is very important? Because Gauss's law, if we apply the Gauss's law, so if you see that if you want to calculate electric field at point P or any point, okay, so we now calculate electric field. That very easy technique is if we apply the Gauss's law here. So that is very easy. When you apply some electric field, vectorial addition, vector multiplication, addition, so there is too much problems here. Okay, there too much burden. The Gauss's law simplify all that. You forget all the vectors concept. You forget all that addition, subtraction, electric field concept. Not forget. Okay, so if you all that complicated tasks, now the simple apply the Gauss's law. Simple apply the Gauss's law. Okay. So how to apply the Gauss's law? To choose a arbitrary field actually. Okay. So today I discuss application of Gauss's law. You see that just application of Gauss's law tells that simply you put some fundamental in that equation or fundamental concept or fundamental assumption, and you can calculate electric field very easily. You can skip that integration, differentiation, complicated terms. Okay, ignore that. So Gauss's law again. Recall the Gauss's law or same topic discuss again. That is a surface. Okay, and there the surface enclosed by positive charge Q. Now consider small amount of area. Name that area is delta A, and know that the area vector, the perpendicular to the surface delta A, and this is a positive charge. Okay, so electric field outward direction. Okay, so we know that Gauss's law, that is equal to delta phi flux, that is equal to E dot delta S actually, that is phi, that is flux concept. Now derive the Gauss's law from flux. From flux, we just some step we added here. We know the electric field, that is Q source charge or enclosed. This is a Gaussian surface actually. Gaussian surface. If you want to calculate the electric field at that point, if you want to calculate electric field at that point, so simple apply Gauss's law. So Gauss's first step is choose any arbitrary closed surface. Okay, choose any arbitrary closed surface, and now apply Gauss's law. First choose any arbitrary closed surface and calculate electric field at that point or line of the surface. Okay, actually means the circumference. Okay, so Q 4 pi epsilon naught the r square, the distance is r cap. So not r cap actually, that is not vector, that is the r distance. Okay, the radius of the circle is r, and the delta is, now we integrate this. Okay, actually, so integrate this or delta terms into ds, and that is E that is the vector r cap unit vector. So E obviously r cap unit vector, and that delta S or delta A here, delta S or delta A both are the same. So delta S and r cap represent the electrical, both are in same direction, means a cos 0. So Q over 4 pi epsilon naught r square cos 0 degree, you know cos 0 be the 1. So here suppose the cos 0 be the 1, q by 4 pi epsilon naught r square. So r delta s, and r is a unit vector. Okay. So we know that r is a unit vector, so the value of r is the 1. Okay. So r equal to 1, you say that is a unit vector. So q over 4 pi epsilon naught r square, and that is a dA, the integration, that is a d phi integration, that is equal to phi. If I integrate d phi, you get phi. So now these are all constant actually. The q over 4 pi epsilon naught r square and integrate ds, that is we get a s. The q over 4 pi epsilon naught r square s. So s represents surface, and that is a 3D object actually. So the curved surface area of sphere, surface area of sphere, and you know that 4 pi r square, that is equal to q over 4 pi epsilon naught r square and 4 pi r square. R square cancel, 4 pi cancel. So finally get q by epsilon naught, that is equal to phi. That is the Gauss's law. The total charge enclosed by the surface, it is a q by total surface. No, sorry, not by total surface. That is a q, the total charge enclosed by the surface. Yes, and it's a permittivity of free space actually. That's the Gauss's law. Yes. Able to find, calculate electric field. Here are some important points on Gauss's law, and you always note that the important points. Okay, the first important point is some important points on Gauss's law. Some important points on Gauss's law. Okay, and these also in NCERT book there's some points also. Okay, so semi point actually write down the notes from NCERT books and actually summarize that huge topics. Okay, so you summarize on 2-3 lines. First point, the some important first point is that Gauss's law, this law in terms for many, in terms for in terms for any closed surface, any closed surface, no matter what is shape and size. What is shape and size. Number two, the terms Q, charge Q on the right side of the equation, side of Gaussian equation included sum of all charges, sum of all charges enclosed by the surface is by the surface. The charge may be located anywhere inside the surface. The charge located anywhere inside the surface. Yeah, surface. Number 3 point. In the situation when the surface is so chosen, when the surface is so chosen that there are some inside that there are some inside and outside the electric field. Okay, so actually charge, say that it is charge anywhere enclosed by the surface, anywhere, not in center, any point. Okay, actually the surface is like this. Charge of this plus charge here, or charge here, or charge here, not mean at center or mass center, anywhere, inside or outside. Okay, if the outside, that's the important place on electrical here, some point electrical here. If the charge is plus q here, some due to that there is some electrical here. So that means here that point electric field may be differ by these and these charges. These two charge affect the electric field at that point actually. Mhm. The electric field on the left side, electric field on the left side mm, is due to the all charges, is due to the all charges both inside and outside, both outside. Number 4 point, the surface is chosen, the surface is chosen for the application of Gauss's law. uh, Gauss's law is called the Gaussian surface, called Gaussian surface. Number 5, the Gauss law, this law is often uh, useful towards towards much easier calculation of the electrostatic field. Calculation of the E field. I told that. That is a Gauss law is useful for calculate electrical actually. Main purpose of Gauss law is that calculate electric field. Okay. So number 6 is to choose an Gaussian surface very carefully. Choose an Gaussian surface very carefully. Okay, because charge try to cover the charge enclosed by the surface. Number 7. So actually Gauss's law depend on inverse square law. Gauss's law depend on inverse square law. Like a Newtonian law, okay. Actually the inverse square law dependence. So actually they indicate the departure from the inverse square law, okay. Clear? That's the Gauss's law and significance of Gauss's law and what is the importance of Gauss's law. Okay. So today end the class here. Thank you. And next class we discuss application of Gauss's law.